Today we're going to have a look at the third part of the radiation topic of National 5 Physics, nuclear reactions and power. And we'll start looking at nuclear fission reactions. So a nuclear fission reaction happens when a neutron is fired at a large nucleus, causing it to split into two. This splitting creates two smaller nuclei, some more neutrons, and a very large amount of energy. Now, that reaction can self-sustain itself in what's called a nuclear chain reaction. So, the first neutron that comes in creates one nucleus which splits and releases neutrons. These neutrons can then go on to create further fissions with other nuclei. That's known as a chain reaction. So as we can see here in the little animation, the first neutron comes in from the left-hand side, splits the first atom, splits the first nuclei rather, releasing three further neutrons, which collides with three further nuclei. Each of those nuclei then split, releasing three further neutrons, which can then collide with three further nuclei, and so on and so on. Now, this process happens in a nuclear reactor, like we might find in a normal nuclear power station. The reaction happens in these orange bars called the fuel rods. The fuel rods, they are contained within this grey material called the graphite moderator. There are control rods which slide in and out of the reactor to control the rate of the reaction, and there is a coolant which passes through the reactor, cooling the reactor and taking the heat generated out, which can then be used to generate electricity. The whole thing is contained in this green containment vessel, which is usually made of thick concrete to stop any radiation from leaking into the environment. So, fuel rods, they contain the nuclear fuel where the chain reaction takes place. The moderator slows neutrons down to make them more likely to cause fission. The control rods absorb neutrons and they slow the reaction. They can be raised or lowered to control the rate of the reaction. The coolant, usually air or water, comes in through the bottom of the reactor, heats up, absorbing heat, stopping the reactor from overheating, and then the hot gas is then used to power the generator. And it's all held within the containment vessel, thick concrete, to contain the high levels of radiation created in the reaction. So here's a little working animation of the whole process. We can see the coolant entering the bottom of the reactor, passing over the uranium fuel rods, in which a nuclear chain reaction is occurring, and then the hot coolant coming out of the top of the reactor. That then passes through the boiler, which heats up water until it boils, creating steam under pressure. That steam under pressure comes out the top of the boiler and forces a turbine to turn. That turbine then drives the generator, which creates the electricity. The steam is then cooled in the condenser and returns in this loop to be heated again, and the reaction continues. Now, there are a lot of pros and cons of nuclear power. Nuclear power provides a stable, reliable energy source, not dependent on weather. A small mass of nuclear fuel will provide the same amount of energy as a large mass of fossil fuels. And it doesn't release greenhouse gases, so nuclear power doesn't really contribute to climate change. The downsides of nuclear power is the risk of nuclear accident, which could harm a large number of people. The fact that uranium itself is not a renewable source of energy, we will eventually run out of it. Nuclear waste that's created in the reactor remains highly radioactive and very dangerous, therefore, for thousands of years, so it's very difficult to store. And finally, weapon-grade plutonium can be produced as part of the reaction. Now, There is another type of nuclear reactor called a nuclear fusion reaction. Now, in nuclear fusion, rather than a large nuclei splitting apart, two smaller nuclei, typically hydrogen isotopes, are forced together. When they are forced together, they make a larger nuclei, and that also releases a lot of energy. This is the reaction that happens inside of our own sun, and in fact, all stars. Now, there are a lot of advantages to nuclear fusion over nuclear fission. It's safer, produces much less harmful radioactive waste. The fuel is very easy to acquire. In fact, it just requires hydrogen, which can be taken out of seawater. And there isn't any ability to create materials used for nuclear weapons, which makes it a very, very desirable fuel option. Unfortunately, nuclear fusion is very difficult to do. The reason for this is the neutrons have to be forced together under a huge pressure. And that requires heating the plasma, which is the fuel, to extremely high temperatures, 100 to 200 million Kelvin. And in order to achieve these temperatures and maintain these temperatures, you have to isolate the plasma. So it has to be confined for at least 4 to 6 seconds. And that's very, very difficult to do without expending more energy confining and heating the plasma than you actually get out in the end. A lot of groups are working very hard on this at the moment using magnetic confinement techniques, and it's probably only a matter of time until a working, efficient fusion reactor is brought online. But it's very difficult to do, and as yet hasn't been made as a reliable fuel source for us. So that brings us to the end of the nuclear reactions part of the course. You might want to try some past paper questions, so you can click on the link to the second video on the description of this video and find out about those. But until next time, bye for now.